So we shall begin with presentation 01, Simulating MapReduce Application Performance on Scalable Clusters by J.R. Gray and T.C. Bressod, Department of Mathematics and Computer Science, Denison University, and the presenter is Mr. Gray.
Well, hello everyone, and thank you for coming. The subject of my research for the summer is MapReduce, a programming runtime invented by Google. So let's jump right in. First of all, what is MapReduce? So suppose we have the following scenario. You're given a book and you want to create a word frequency histogram. So you want to count up all the words in the book and chart them out. How might we accomplish this? Well, in computer science, there would be a very simple algorithm that we could go about making that simply counted every word in the book. And if we hadn't seen the word before, we would initialize the count to 1. And if we had seen the word before, we would increment the existing count by 1. And that's fairly straightforward. But if we have a lot of data, this might not work out so well. And this is a real-world problem because we generate data far faster than we can actually analyze it. It's a big problem in the IT industry. For scientific applications, we have experiments that generate all kinds of data, and we need to analyze it fairly quickly. So how do we go about solving this? Well, Google came along and invented MapReduce, which in our example here would be a very easy way to take our algorithm and run it across an entire cluster of computers in a distributed fashion. So with MapReduce, we have some notion of input data, which in this case would be a book or a series of books, maybe even an entire library, or every book ever written, doesn't matter. But that input data goes into the map phase of MapReduce. There are two main phases, map and reduce. In the map phase, we have a series of map tasks. These are computers running a user-specified algorithm. So what might this look like in our book example? Well, MapReduce would take our book and it would partition it into sections automatically. And then it would allocate a section to each individual mapper computer or computer running a map task. And then the mappers would run this user-defined algorithm on the data, which in this case would be the algorithm we defined earlier, and save the results of that algorithm to local disk. And the format of that output will be a series of key value pairs in this case, where the keys are the words and the values are the count of those words. So the output of the map phase is a series of key value pairs saved across the local disks of all the mapper computers. And MapReduce invisibly kind of shuffles these through a phase called the shuffle and sort phase, which reorders the key value pairs, aggregating them to some extent. And these reordered key value pairs go into the reduce phase, which, similar to the map phase, is constituted by a series of reduced tasks, again running on a series of computers. So if in our book example we were to do this, we would be pulling the data in from each disk of the mapper computers to a reducer computer. And this reducer would run an algorithm to combine the results and form a complete histogram. So in this case, you might imagine the word the appears in every chapter of the book. So we have multiple counts for the, and we need to sum those up before we can actually get the histogram complete. So each of the reducers are going to save their output data to their local disks. And once you're complete with the MapReduce application, you would then poll each of the reducers and pull the data in whatever fashion you please. So that's kind of how MapReduce works in a nutshell. My research specifically focuses on MapReduce performance. Namely, we might expect, kind of naively, that if you increase the number of machines running these MapReduce tasks, that the execution time will decrease in a fairly linear rate. So if we're running on one machine as opposed to two, we might expect roughly half the performance, but that just simply doesn't happen. In fact, the performance characteristics of MapReduce aren't very well known, in part because there are so many performance characterizations to make of the runtime. So a few considerations. Number one, there's a horde of parameters. The size of the input data that the mappers are reading in, the amount of data they're writing out, the intermediate data in other words, and the amount of data that the reducers write out. The number of files accessed and created. There's a certain overhead with managing all of those. there's a scheduling algorithm, kind of invisible to the user, that actually distributes the tasks across the cluster. That can have huge performance impacts, as shown in previous research on heterogeneous clusters. And there are so many, many others that I couldn't possibly mention them. But one of the really important ones is failures. And failures can affect performance dramatically when they occur. And to make matters worse, the failure rate assumptions that are made in theoretical research are often inaccurate. For instance, it's often assumed they follow a Poisson distribution when they may not. And one thing that complicates our research is that actually running MapReduce applications is immensely time-consuming. If we wish to characterize the performance of MapReduce, we can't sit around and run applications all day. It'll just take too long. So the goals for the research were first to engineer MapReduce benchmarks to kind of give us an idea of what the most important performance characteristics are. And then once we have some of that data, we can create a model that's more robust than those that exist in previous research. And specifically, we want to devote specific attention to the shuffle and sort phase, which has often been left kind of out of the picture in previous research. Next, we wanted to develop a simulation for MapReduce applications. Very importantly, we wanted that simulation to be able to incorporate realistic failure behavior. And we actually got real-world failure data from Los Alamos National Labs, which keeps a record of up-down intervals on a series of cluster computers. So in modeling MapReduce, which is kind of the meat of the work, and then making a simulation that respects that model, there's a lot to be done. So first, on the benchmark side, I'm not going to show you all the benchmarks for the sake of time, but here's an example. So this benchmark just shows us the result of this was that we found for every 34 additional map tasks we create on our cluster at Denison, we got a roughly 3.7-second increase in runtime. So this gives us an idea of the overhead of creating individual map tasks in a very naive fashion. And there are many other benchmarks that I won't get into, but that's just one. Okay, so as for the new model. So here's a map task. This is our model for the map task. And we have kind of three main states: active, inactive, and complete. So if a node is active, that means it's doing some kind of work. That work is split into three substates, if you will: read, work, and write. So read would correspond to the amount of time required to read data in from local disk. Work would be the amount of time spent in the user's algorithm, and write would be the amount of time writing out to local disk. Now, as I mentioned, the simulator is going to incorporate real-world failure data. So if a failure occurs while the node is doing any of this work, then it actually goes down. And the way MapReduce handles that is it re-executes the task entirely from start to finish. Should that not happen, or should the task eventually make it through all the states, it will become complete. And it's complete, we're done. The reduce task is very similar. It has the read, work, and write phases, but it also has an additional sort phase meant to encompass the shuffle and sort aspect of MapReduce. Technically, this is handled a little bit both on the map and reduce side, but for the sake of simplification in the simulation code, it's represented here. So again, same deal. If there's a failure that occurs, the node goes down, and we have to re-execute from the beginning. And then we have the application model. This is kind of dictating what happens when you run a MapReduce application from start to finish. So first, there's a map phase, and part of it executes. So we wait for all the mappers first to complete the read, work, and write phases. And once we're at that point, the reducers begin to read in the data from the remote mappers. And this is realistic of what happens in MapReduce. Once all the reducers have read in the data, they begin sorting, working, and writing. And remember that if any individual tasks fail, they have to start over again. So we may spend more time than you would expect in each of these phases. And finally, once all the reducers have completed their sort, work, and write, we complete the map and reduce the tasks in the simulation. Now, this new model introduces a new set of opportunities for things to fail compared to previous models that have been created. For one, if a mapper fails before all the reducers complete their read, then we have to re-execute the mapper. And so basically that entails resatisfying the condition that all M mappers have completed read, work, and write. And so then that kind of entails pushing us all the way back to the start, back to square one. So that is a potential issue that can come up. And kind of a bigger issue that can come up is if we have a mapper and a reducer fail, we get an application failure. And the reason for this is that we assume in our model kind of a uniform key distribution on the map side. So in other words, the mappers, we assume, are going to create a set of keys such that all the reducers are going to need a key value pair from, at least one key value pair from every mapper. So if a mapper should fail, after the reduce read is complete, MapReduce will not re-execute mappers. So should a mapper fail and then a reducer fail, the reducer will have no way to get back that key value pair that was lost. And so the application overall fails. So that's the new model. It's more realistic in terms of the failure behavior of MapReduce, and we think it's a solid upgrade to what's already out there. In the future, we want to examine the role of networking. This is very important on the write and read phases, especially remote reads on the reducer side. And we want to look at the statistical properties of the MapReduce performance as we scale the number of mappers and reducers, the number of machines, and the number of processor cores. And then we want to look at distributed file system performance. That's not something we really addressed here. And a more efficient simulator is kind of key because the simulator itself, as you may imagine, is quite complicated. And we need to kind of tone it up a little bit. So that's future directions. Thank you for having me here. Yes.
What's the runtime like?
What is it like?
Yeah.
Well, not sure what you mean by like.
What is the runtime of one of these simulations?
Oh, I thought you meant runtime. You can have runtime as two separate words or one word. Yeah. The simulation, it depends on the number of tasks running primarily. So if you're running it on just a few, maybe a dozen machines, that's going to take virtually no time. But if you're scaling up in the hundreds, it can take quite a while. In fact, my advisor, Dr. Versu, was running it, a previous instantiation of the simulator on a month's worth of work, and it took about a week to run with a really large number of tasks running. So it has a significant amount of overhead potentially.
So how do you simulate the failures? Is it like a random things might go down kind of thing?
Well, the data we have is pulled from real-world clusters. So the data is of a format where we have up-down intervals, and the machines are allocated, or the tasks are allocated on processor.
You're analyzing real things that really ran on real MapReduce.
Well, it's not. I don't know if the cluster was running MapReduce, but the failure data is real. And actually,
so, yeah, the cluster is real. It's from Los Alamos National Labs, and it's their own clusters that are most likely the kinds of scalable clusters we're interested in, but their applications are not MapReduce applications.
yeah, and actually in Versu's 09 paper, it was shown that the failure distribution for that data followed much more closely with a beta distribution than any other. So it's interesting to look at real-world data as opposed to the theoretical assumptions about what the failure rate might be.
No more questions? Well, thank you.